1.10, the last lesson in this chapter. It's on mathematical modeling and variation. So we're given some data, and we want to make a scatter plot. And this is the data is the median purchase price for homes in the U.S. from 1990 to 1996. We want to make a scatter plot of these data and draw a linear line through the data as best we can and come up with an equation for that line. Okay, so first I look at the price. Ranges from $131,000 to $153,000. So I want my scale. By the way, this is going to be our X values and our Y values. So the price is the Y value. So 30 different units. If I go 15 squares, then I can go by twos. And on the X, I've got 1, 2, 3, 4, 5, 6, 7. So I can make a plot 15 by 15, and then then I can do the scaling. So let me draw a line for the X, Y axis, and let me draw it for the X axis. Now, I said I'm going to go every two, so the bottom one would be 130, and then this would be 132, so on and so forth, 34, 36, 38. Here's 140, 2, 4, 6, 8, 150, 2, 4, 6. Yeah, let's see, this is 156. Okay, now on the year, I'm going to go from 1990 through 1996. So I'm going to make the first one 1990. And then every two squares is another year. So here's 91, 92, so on and so forth. 93, 94, 95, 96. So here's 1996. Now I can start plotting these. Okay, the first one, 1990, 131. So that's going to be right here. 91, 134. 2, here's 134. 92, 141. So it's going to be here. 93, 142. 94 is 145. So here's 94. 145 is right there. 95, 148. Here. 96, 153. So right there. So I've got the data plotted. You notice it's not quite a straight line because it looks like in 92 we had quite a bump up. So we have to take that into consideration. So I'm going to just estimate kind of a best straight line through most of the data points. So I'm going to start off like, say, 132, and I'm going to come up and kind of make it like that. This is kind of a guess. You notice that the line doesn't have to go through any of the points, but it's going to be the best fit line just looking at it. And now we're going to see what the equation of the line is. So in this case, we do have y-intercept. So I'm going to use y equal mx plus b, because I know what b is. B is 132, which is the y-intercept. So now I just have to find the slope m. So the best thing to do is go and find a couple of points that are kind of on a line. So let's say, say one point we're going to have this one in green in 1991. And then let's go in 1996, let's use the point that's there. And now we want to write the coordinates. So let's use that. Let's use this point right here. Actually, we want a point on the line. I think I was doing some of these, I erased them, so let's try it again. So 2 points on the line is going to be this value in 92, and let's see, 95, let's call it this value. So now we just want to put coordinates. And so we have 92, and say 139. And the coordinates of this would be 95, and let's say 149. So now we can get our slope. So slope equals delta y over delta x. Change in y is 149 minus 139. Delta x is 95 minus 92. So 149, so that's 10. 95 minus 92 is 3. So our slope is 10/3. So now we can come up with an equation. Y is equal to mx plus b. Y equals 10/3 x plus our b we said was the y-axis coordinate 132. So here's the equation of the red line. And if we wanted to know or project it out to be year like 2000, we could just put 2000 in for x and find out what the average selling price in the year 2000 would be. Now, there are a lot of graphing applications or utilities that will actually do a scatter plot for you and draw in a trend line and give you the equation of the line. Not every line is going to be linear like this one I drew. You could have a logarithmic, or you could have some exponential, or a power series, any number of different types of scatter plots with the different lines. We're not going to get too heavily into that. I just wanted to introduce it to you because this is useful for some of the plots that you may be making, like in chemistry. But for now, we'll just leave it at that, and we'll just move on to direct variation. Okay, direct variation. Direct variation, it's a model for linear equations. We just went through one, talked about one, y is equal to mx plus b, but a simpler one would be y is equal to kx. And this means that y is directly proportional to x. It's directly proportional to x. And the k stands for a constant. So in this example, we have we're going to have a $2,500 investment. And well, I wrote 25,000. Okay, there, 2,500 investment. And the interest after 1 year, the interest we earned, is $182.50 interest. And we're going to call this I, and we're going to call the investment P, capital P, for principal. And so now we need to find an equation where we're going to solve for interest. Well, it comes after, or the model, y equals kx, but in this case, our y is going to be the interest, and the x is going to be the principal. So we're going to rewrite this as I equals kp. Now we want to solve for k, because we have p and we have I. So solving this for k, we divide both sides by p. So I divided by p is equal to k, and this is our constant. And so this is equal to 182.50 divided by 2,500, and that gives us 0.075. Once we have solved for the k, then we rewrite the equation using the k, and so this original I equals kp becomes I equals 0.075p. So this is our formula, and for any given principal, then we can calculate what the interest is. Okay, we also have a direct variation when we raise x to an nth power. So this could be something like y equals kx cubed, or kx to the fifth, or any power you like. And the reason, I don't think I mentioned earlier, the reason I call this direct variation is because the value of y varies directly with the value of x. In other words, if the value of x goes up, the value of y goes up. the value of x goes down, then the value of y goes down. So let's look at a typical example. This is a physics problem. So for a falling object, the distance traveled varies directly as the square of the time. So we want to come up with an equation that says varies directly as the square of time. So our equation is going to be y is equal to k, but instead of x, we're going to use t because that's time, and it varies directly as the square of the time. So y equals kt squared. So this is the form of the equation we're going to use, and here's what we're given. We're given an object falls 144 feet in 3 seconds after it's been dropped. I want to write an equation given these data. Okay, so we're going to start off with the general equation, y is equal to kt squared. Now we're going to fill in the blanks. Well, we want to solve for k, so let's go ahead and do that first before we put numbers in. K is equal to y over t squared. And we're given that y is 144 feet, and the time is 3 seconds, so t equals 3 seconds. So we just put that into our formula. We get k is equal to 144 feet over 3 squared, which is, I'll just write 3 squared, but if you square that, it's going to be, you're squaring the units too, so it's 3 squared, second squared. And so if we divide that out, k, 144 divided by 9 is 16. The units are feet per second squared. Once we have the value of k, then we put it back into the original equation. So I'll write that in red. So y is equal to k, which is 16, and t squared is the equation you came up with after you solved for the value of k. Okay, now we're going to look at inverse variation. So the formula is y is equal to k divided by x. So what this means is y is inversely proportional. Inversely proportional to x. So what that means, if the value of x goes up, the value of y goes down. If the value of x goes down, the value of y goes up. So that makes them inversely proportional to each other. Okay, here's an example of inversely proportional. We know that the demand for a product varies inversely to the price of the product. So typically when the price goes way up, the demand goes way down. This usually is normal for most products. I would say some Apple products are probably immune to this because people will pay whatever it takes to get the new Apple device. But for most things, this holds true. So here's the problem. We're given when the price of a product is $2.75, the demand is 600 units. We want to write an equation relating the demand and the price. So we're going to start off with our equation for inversely proportional. Y is equal to k over x. Now here's what you need to figure out. What do you call k in this case? What do you call y, and what do you call x? Well, we know that x is the independent variable, which means it's the one that you can control. And the y value is going to be the dependent variable. Well, the independent variable in this case is the price. You can change the price, and then whatever the price is affects the demand. And so the demand in this case is the dependent variable. So we're going to say P is the price, which is the independent variable, and that is $2.75. And then we'll call it D for demand is 600. So we're going to rewrite the y equals k over x to be d equals k over p. And we want to solve for k. So we have to multiply both sides by p. And let me take this and start again over here. So I'm going to say k is equal to d times p. So then just plug in the numbers. 600 times 275, and that gives you 1650. So now that you have your value of K, you rewrite the original equation, substituting in the value. So that gives us D is equal to 1650 over P. Now that we have this equation, we said, what if the price is $3.25? How many units are you going to sell? So we'll put that down. What if, make it in red, what if you raise the price to, say, $3.25? Well, you would expect that the demand would be less. So using this equation, demand is equal to 1650 divided by the new price, which we said is $3.25. And that gives you 508 units. So using the equation we found, D equals 1650 over P, we can find the demand for any given price. Okay, now we're going to look at direct and inverse variation. First equation, y is equal to kx over p. This means that y varies directly as x and inversely as p. Now we're going to add a joint variation. So look at the first one here. Z is equal to kxy. That means that z varies jointly as x and y. Next one, z is equal to kx over y. That's z varies directly as x and inversely as y. And then the last one, z is equal to kw x squared over y cubed. So this means that z varies jointly as w and the square of x and inversely as the cube of y. So let's do an example like that, an example equation. So here's our example. This is actually an engineering problem. Write an equation for the maximum load, and that we'll call L, on a horizontal beam that is jointly proportional to its width and the square of its height, and inversely as the length of the beam. Okay, so L, which is the load, is equal to, always need a K. Now it says directly proportional to its width, so that's kW, and the square of its height, so that's going to be h squared, and inversely proportional to the length of the beam, so we'll call it little l as the length of the beam. Okay, so what does this mean? So if the width is doubled, then the load is doubled because they're just jointly proportional. But if the height is doubled, you got the height squared, and so the load is quadrupled. And so it's like double squared, 2 squared is 4. So the load is increased by a factor of 4 when the height is doubled. What about if the length is doubled? Well, if the length is doubled, that's little l. That means the load is reduced by a factor of 1/2 with the length doubled. Okay, so that's it. Actually, that's it for chapter 1. And so next comes a little bit of homework and then some review and a quiz, some more review, and then a chapter test.